Okay. Yeah. Far out was out there, and so the three laws were, one, that everything is an ellipse. And if you've never done it, you can actually draw an ellipse by getting your two focuses, have a string tied to the focuses. So your string is string is a constant length, but as you go around, you get a nice elliptical pattern. So my ellipses, I don't draw ellipses very well, but it turns out that the Earth is one of the reasons why people always thought circular orbits. It turns out Earth is really close to being a circular orbit. So that's the first one. The second one talked about how if you were drawing those here's the sun, and you were doing a sweep of the area, that these areas would have this, or these areas would be the same. So that was another of Kepler's observations. And then the third one said that this was a constant, that the period squared was the period squared over the nominal radius cubed was going to equal some sort of a constant. But that's a little misleading because our orbits aren't really round. They're elliptical. So, and because they're elliptical, we have those terms that, so if I have an ellipse, I'm going to have, and I want to make sure I get it straight because I can always get them confused.
What was that equation? T squared over what?
R cubed is a constant. That's Kepler's third law. That we have what's known as perigee, and that's when we're closest to the foci, and apogee is when we're farthest from the foci. So when we talk about this last month, we had a supermoon. That's because the moon was at perigee in the orbit, and we were getting it at its closest point, and hence it's going to look bigger than when it's at apogee, its farthest point. So I get perigee and apogee. And if I want to do something fun and look at the International Space Station, the ISS, because it's been in the news lately, the orbit, the period, or the period of the orbit is 92.68 seconds. So the International Space Station orbits the Earth every 92.68 seconds. It has, at perigee, it is approximately 403 kilometers away. And at apogee, it is at 408 kilometers away. And so we do have perigee and apogee. Now we do have a force due to gravity. There is an acceleration due to gravity on the International Space Station. They aren't completely weightless, and we can actually calculate that. So we'll play with that here in well, actually, the acceleration due to gravity. Oh, well, let's get to the next spot. So Newton's law of universal gravitation, which we usually use as F sub g, it's going to be a big capital G, mass 1, mass 2, divided by the radius squared. And we're going to see that behavior a lot. So we're going to talk about that here in just a second. But let's look at G on the ISS. Because if I look at this, what I can break up is G, mass of the Earth, radius of the Earth, m2. This is going to equate to the acceleration due to gravity. So if I do that on the surface of the Earth, so let's do it on the surface of the Earth. And one of the reasons I brought my book today is because I wanted to show you a couple things. So first of all, the mass of the Earth, according to our book, and by the way, our book uses this symbol right here to mean mass of the Earth. A little cross sign in there. And the mass of the Earth is 5.9736 times 10 to the 24th kilograms. The radius of the Earth, and again, our book uses this little cross thingy in there for the radius of the Earth, is 6.378 times 10 to the 6th meters. So if we're going to calculate an acceleration due to gravity, it's going to be 6.67. Oh, do I want to change that? That's physical data. That's astronomical data. 6.67. We'll go ahead and do it as 4 times 10 to the minus 11 Newton meters squared kilogram squared. Oh no, that's not little g, that's big G. Because we needed big G, sorry. So little g is going to be big G, mass of the Earth, radius of the Earth squared. So now I get my 6.674 times 10 to the minus 11 Newton meters squared kilograms squared. And I get this number up here, 5.97 times 10 to the 24th. And then I get my 6.378 times 10 to the 6th. And that all has to be squared. And we plug that into the calculator. 6.67. Clear everything. 6.67. Put that number in there. 9736. That gives me on top 3.987 times 10 to the 14. 6.378. And this gives me 9.80. And let's do the unit analysis. So I have Newton meters squared, kilograms squared, and I have kilograms meters squared. 1 kilogram cancels, meters squared cancels, so now I get kilograms meters second squared kilograms. Kilograms cancel, I end up in meters squared. And this is 6.378 times 10 to the 6th. All that squared. And it gives me 9.8. So now if I want to do G on the space station, so let's look at G, the gravity on the space station. R is going to end up being 6.737 times 10 to the 6th meters plus, and we're going to do, and at the space station, the average is about 405, right? If I do 408 and 403, I get an average about 405. So I'm going to do 405, and that's 405 kilometers. So I got to add those lovely digits. Gives me something like 6.783 times 10 to the 6 meters. So now G on the ISS is going to be 6.674 times 10 to the minus 11 Newton meters squared, kilograms squared. Mass of the Earth, 5.97 times 10 to the 24th. Divide by 6.783 times 10 to the 6th. And that's got to be squared. It's actually about 8.6 times 10, no, 8.6 right there, meters per second squared. So there is gravity on the International Space Station. They just are moving relative and they don't necessarily get a chance to see it, because they have another acceleration on them. So we can do those fun calculations. So our chapter starts out with Kepler's law. Ultimately, we talk that there was the apple and the moon problem, and we got a chance to see the apple and the moon problem on in the video. I'm discussing the video, but here's one of the things that we also have talked about is that my centripetal acceleration is equal to v squared over r.
Pull it down, please.
I got it. Then we get the centripetal acceleration is v squared over r. This gives us, and this is where we were a week ago today, talking about bank turns and getting why we have bank turns and having that acceleration v squared over r. So we end up with that aspect, and that's where we start talking about the apples and the moon problem. But then we also have our good old gravity problem, and this is our universal law. In between any two objects, I'm going to have that relationship. And it turns out we can actually work with this and look at a variety of different systems when we are playing with that. But one of the things that we also want to talk about is we've also talked about forces. So if I have a box and it has a mass, I apply a force to the box, either a push or a pull. This we refer to as a contact force. It's a force that's resulting due to that push or pull. Gravity is a little different. Gravity is what we call, so if I have my Earth here, and I have my little mass here, it's going to fall towards the center of the Earth. And there is no contact on that mass that's causing it to fall to the center of the Earth. This is falling to the center of the Earth because of that right there. Okay? It's also, we can also say that it's pulling on the Earth as well, but because of the difference in the masses, you're never going to see that. And this gives us something that we call a field force. Okay? We can get a field force. So the sun has a field force. The moon has a field force. We all have, so we have these gravitational fields. And when we start talking about Einstein and Heisenberg, and they talk about the warping of space, and I think you all have seen it, right? You've seen the demonstration. If not, I'll start digging it up. Where they take a trampoline. So I got a trampoline. And in one spot, they put like a medicine ball. Okay, a medicine ball that you'd play at the gym, And we know what happens to the trampoline when that medicine ball comes in. We start getting a topographical map. It's not a plane anymore, that the ball actually is sinking in. And then I can put in another object, say a bowling ball over here, and it also gives me a depression in the trampoline. And I can take a tennis ball at that point and roll my tennis ball with a given velocity that it will bend and might get caught and sink in around that particular object. And I'm sure people have seen it because Nova's done these videos, or a bunch of videos out there that show that. And so this gives us how gravity kind of distorts space. But on Earth, we see it as a field force. In space, we see it as a field force. But to really explain this, we have to go a little bit more towards what Einstein's theory is, rather than Newtonian. However, Newtonian mechanics will get spacecraft outside of the solar system. So Newtonian mechanics works really, really nicely. So we don't necessarily have to have that that explanation to actually get things out of our solar system. So a couple of other things is that even though we write that this force due to gravity, we've written it like this, we know that forces are vectors. And so if I'm dealing with my Earth problem, and now I have my force due to gravity, it's going towards the center of the Earth, no matter where I am on the Earth, I can draw what we call a force field. Okay, so we actually can get a force field, and we can get that and draw that in. But when I'm looking at this, if I have just two objects, and my object happens to be the Earth and the Moon, the force that you're seeing is along this R between the two objects. Okay, you're seeing that force along that distance between the two objects. So if I'm looking at the force between the Earth and the Moon, it's always going to be along that line. So when I'm starting to look at net forces due to massive objects, I've got to be cognizant of where this line is, and we'll actually work a problem here in just a second on it. So you get that line of attraction. The other thing that it looks at is that the force due to gravity is going to be proportional to 1 over r squared. So if I'm looking at the Earth, and I've got a force due to gravity, so I'm going to just kind of look at this, and as I move away in distance, so I'm moving away in distance r, I'm going to start with a force due to gravity at the surface of the Earth of 9.8, proportional to our 9.8 meters per second squared, because it's proportional to the force, but the magnitude is going to fall off as 1 over r squared. And we're going to see this 1 over r squared relationship in a number of different ways. And since most of you have had general chemistry, most of you have seen this one. Good old Coulomb's law. Because we talk about electrons and protons. But look at the forms of those two equations. They look the form of those two equations look very, very similar, and the force falls off as 1 over r squared. So we see a lot of similarities that are out there. So let's find the force due to gravity between the Moon and the Earth. So we're going to do the force due to gravity using the universal law. And this is going to be a magnitude because we know the line of action, so I'm just calculating the magnitude. That's going to be 6.674 times 10 to the minus 11 Newton meters squared kilograms squared. And the mass of the Earth, 5.9736 times 10 to the 24 kilograms. Mass of the Moon, 7.35 times 10 to the 22nd kilograms. And our distance, and this is going to be multiplied, and our distance is 3.84 times 10 to the 8th meters, and we have to square that. If I plug that into the calculator, and if I've done everything correctly, I get 1.99 times 10 to the 20th newtons. Because meters squares cancel, kilograms squares cancel, I'm left with newtons. Now, have I walked with you guys through exponents? Because some of you have the other calculator. And the other calculator gets funky when you start playing with exponents. I'm going to borrow your calculator for a second, Madison. Some of you have this calculator, which is supposed to be the newer version of that calculator. This calculator handles exponents very differently than this calculator. So let me make the background a little cleaner. Okay? So, and so this is why I suggest that you guys be careful. So I'm going to put in 6.674. I have to turn it on. There we go. 6.674. There's this minus 11. So that's how that calculator is going to show it. But to do it on this calculator, I have to do 6.674. Is it the up arrow? Yeah. Or, wait a second. There it is. Second function. Oops, I got to do the other one. You can do it. There's a couple of different ways on this lovely, lovely one. You want to do it that way? No, that's an exponent.
Is that not what you're trying to do?
Nope. If I'm doing scientific notation, I've got to do times second function and to the minus 11.
Yeah, I usually just type in times 10 and then do the exponent.
Well, that's one way to do it. But that's why I tell you got to be careful, because if I do this and square it, I get that. If I square this one, let's see if I get the right. That one actually happened. No, the numbers are very different.
My calculator's still in scientific mode because I used it.
Well, that's okay. That shouldn't affect this. So you got to be careful when you're playing with it, because if you end up doing this like 6.67 times this to get your exponents, right? And then you multiply it by a different number, 5.9736. Clear. So the key here is you got to pay attention, because if you start putting things in series, it gives you different answers sometimes. And it's because of how this calculator is going to handle the functions versus this calculator. Remember how you handle functions. Exponents first, multiplication, division second, addition, subtraction third. So if I'm putting things into a big long series, I may want to be putting parentheses on this calculator where I wouldn't necessarily have to put parentheses on this calculator, because it will give you different results. So be careful when you're dealing with it. And I've run into that over and over and over again. So that's also a place where you're going to possibly mess up when you're doing your homework on WebAssign. So when you're doing this, so let's look at these numbers. I've got 6.67 times 10 to the minus 11. I have 5.97 times 10 to the 24. I have 7.35 times 10 to the 22nd. And I can do this on the bottom. I can do it a couple of different ways. I've got 3.84 times 10 to the 8th times 3.84 times 10 to the 8th. So I'm doing this into old slide rule days, where I didn't have the calculator that can handle these exponents. If I'm multiplying, if I've got 10 to the minus 11 times 10 to the 24th times 10 to the 22nd, that's going to be minus 11 plus 24 plus 22, which is going to give me 46 minus 11, which is going to give me a 35 for the top. So I end up with 6.67, 5.97, 7.35 times 10 to the 35th on the top. On the bottom, I'm going to get 3.84 times 10 to the 16, because 8 plus 8 is 16. So if I do 35 and 16, that's 35 minus 16. That's going to give me, let's see, there's going to be a 9, and it's 2, it's going to give me 19, right? So my answer is going to be 6.67, 5.97, 7.35 divided by 3.84, 3.84 times 10 to the 19. If I do that and put that in the calculator, where it's a lot less likely to get screwed up because of how my calculator handles the exponents, I get 19.8 times 10 to the 19, which if I put it in scientific is 1.98 times 10 to the 20. And we did it previously and got 1.99 times 10 to the 20. That's a rounding error for not carrying all the significant figures. So it gives you a way to check whether or not your problem gave you, or you punched it into the calculator correctly. And let me double check, because I know what it is in the other textbook. Let me see if they've got it in this textbook. She doesn't have, wait, let me just kind of keep in here, propagation of uncertainty. No, she did not put in this textbook the two things that a lot of textbooks will, and that's the refresher on using exponents and then the refresher on how to handle logarithms. So those are a couple places that you might want to go back and look at, because that's definitely a shortcut to play with when you're working with things. All right, so that gets me to where I want to go, because we want to do this type of problem. So I'm going to take 3 objects. I'm going to take 3 objects. I'm going to have an object M1, and it's going to have a mass of 4 kilograms. It's going to be located at 0, 3. I got to pull this down. Hang on. There we go. I've got a very massive object, M2. It's going to be 10 kilograms. And I'm going to place that at the origin. Okay. And we're going to use these in meters. And then I've got an object over here. This is M3. And it's going to be a 2 kilogram object. And it's going to be located at 3, 1. Of course, we're in meters. I want to find the net force on that object. And then ultimately, its acceleration. So I want to find the net force and its acceleration. So let's look at this for a second and know what's going to happen. So I'm going to end up, we know that gravity is attractive. So this is going to want to move towards that particular object due to its gravitational attraction. This is also going to want to move towards that object due to its gravitational attraction. The force is going to go as 1 over r squared. And it's going to be proportional to the mass. Since this is a heavier mass, this might be a bigger force. But this, we need to know the distances. And it turns out that this distance, so if I do this, I got to calculate my distance, right? So if that's 3 and 1, this line here is the square root of 9 plus 1. This is the square root of 10, which is going to be 3.16 meters. So that's my distance between those two objects. This one, if I look at it, that's 3 this way, so it's going to square root of 9 plus, and then it's going from 1 to 3, that's 2, so that's 2 squared is 4. That gives me the square root of 13. That one gives me 3.6. So now I have the distances between the two, and now I can calculate the magnitudes of the forces. So my magnitude of the force between 1 and 3 is going to equal, and this is magnitude, it's going to be G mass 1 mass 2 divided by the distance squared. This gives me 6.67 times 10 to the minus 11. My first mass is 4 kilograms. My second mass is 2 kilograms. And my distance is 3.6 meters squared. And if I do that and plug it into the calculator, I get 4.11 times 10 to the minus 11 newtons. I'm going to get the force between 2 and 3. It's going to do the same kind of calculation. Except now I'm going to use 2 and 3 and the distance between those two. So I get my 6.67 times 10 to the minus 11. And now I've got 10, and there's my 2, and my distance between is 3.16 squared. And if I plug that in, I get a number that looks like 1.34 times 10 to the minus 10 newtons. But look at that, I can't just add those together because I have vector quantities, and that's the point here. I can't just add them together. So now I need to know this vector. So I have the vector 1, 3. So let's look at that just a little differently here so we can see what's going on. So here's mass 2. I have a vector that's going off here, and we know that this side is 3, and we know that this side is 2, right? Because we had our measurements there. We now know that the magnitude of this is 4.11 times 10 to the minus 11 newtons. So I can rewrite this vector 1, 3 as, now I've got my arrow because we're looking for the attraction on this one, so it's being attracted to that one. So it's going in the negative direction for the I. 4.11 times 10 to the minus 11 newtons. Normally I would put in here, and I'm going to do it in fine little print here so you can follow along. This would be the cosine of the angle, right? And my cosine of my angle is going to be my adjacent over the hypotenuse. And my hypotenuse was 3.16. So this is going to be 3 divided by 3.16. That is an engineering shortcut. I don't have to go in there and actually calculate the angle unless somebody is asking me for it. So it makes it a little bit of a shortcut to actually working when I'm working the problem, and that's in the I direction. I'm going to do the same thing for the y, except now it's 4.11 times 10 to the minus 11. Except now I want the sine of the angle. So that's going to be 2 over 3.16 in the j direction. And if I go ahead and carry out the mathematics, I get minus 3.43 times 10 to the minus 11 in the I direction plus 2.28 times 10 to the minus 11 in the j direction. I can do the same thing for the vector that goes in this way. Except now, this is 1 and this is 3. And that's my F23. And that's my 1.34 times 10 to the minus 10. That's in the negative. Except now I want this one, so it's, and this is 3, oops, I wrote this one down wrong, sorry folks. This one was 3.6. And I just wrote these answers out of my notes, so I'm pretty sure that that's going to be okay. So this is my 3 divided by my 3.16 and the I. And then this one is my 1.34 times 10 to the minus 10. And that one's going to be 1 over 3.16 in the j. And that gets me a negative 1.26 times 10 to the minus 10 in the I, minus 4.24 times 10 to the minus 11 in the j. And now I add the vectors. And if I do the 3, 4, and the 1, 2, 6, it's 9, 6, 4.96 times 10 to the minus, oops, I gotta take care of that, sorry, because that's 10 to the minus 10th. So I take my minus 1.26 minus 10 minus 3.43 minus 11 gives me a negative 1.603 times 10 to the minus 10 in the I. And I get, since this number is bigger than that number, I get a negative 4.24 plus 2.28 gives me a negative 1.96 times 10 to the minus 11 in the j direction. We can calculate the magnitude of the force. 1.6 times 10 to the minus 10 squared plus 1.96 times 10 to the minus 11 squared. Gives me something that's like 1.31 times 10 to the minus 10. And just by looking at it, we know that the net force is going to have it go something like that when we add those two forces together. And we're going to see this type of analysis again. You'll see that type of analysis again. That's just one of the reasons why I wanted to really, really focus on it. I encourage you to go and look at your chapter. They have got some really, really great examples on looking at ignoring the Earth's rotation, doing the analysis. But between last Friday's lecture and this lecture, we finished chapter 7. And we will start conservation of energy on Wednesday. And I think what that's going to give us, just so you guys can start thinking about it, it's probably going to hit a test before spring break. And I think that's better than a test right after spring break. So we're probably going to have a test, I hate to do it to you, at 1:30 on that Friday. But that way we don't start new material that has to be remembered over spring break. And we can go from there. So test will be that Friday before spring break, and then we will be working problems and doing a bunch of other stuff right now.